So today we will study what is called Newton-Raphson method. So before we begin this, so in the previous class, we talk about that photodiode. So as I conclude that, that photodiode is made up of direct bandgap semiconductors, and in that direct bandgap semiconductors, if you connect under reverse bias, if you connect under reverse bias without any illumination of light, the current in the reverse bias condition was very small. That is due to reverse saturation current. And when we illuminate the direct bandgap semiconductor diodes made up of direct bandgap semiconductor, in the depletion region, light photons will be absorbed, and when photons are absorbed, electron hole pair formation will occur along with photon absorption. So these electron and holes, they will follow the same direction as the reverse current, because you are having a reverse. This side is p type, this side is n type. You are having a reverse biasing. So when you connect in a reverse biasing condition, whatever electrons and holes which are formed here, they will contribute to additional current along the same direction as the reverse current. Okay, so therefore, because of the formation of electron hole pair, the current value can increase up to certain value, 100 microampere. If you increase the intensity of light, it can jump even up to 500 microampere. And if you further illuminate it a very high intense beam, it can even go up to 1 milliampere or something like that. 1 milliampere means 1000 microampere. Okay. So depending on the intensity of light, and as long as the light energy radiation photon h nu energy is greater than the band gap energy, the light radiation with which you are illuminating your p-n junction, if the energy of the incident photon h nu is greater than the band gap, then it will result in electron hole pair formation. And the charge carriers will increase, the minority charge carriers will increase, and then you will have a current significantly increase or decrease depending on that. So therefore, even if we have a very faint light, that is low intensity of light illuminating this p-n junction, if the intensity of the radiation is greater than this band gap, the reverse current can jump from this reverse saturation current, maybe around 20 microampere. It can jump from 20 microampere to 100 microampere, or it can even jump to 500 microampere depending on the intensity of light. So this photodiode is a very good sensor, a very good light sensor. Okay, it is a very good light sensor because it can detect even a very small amount of faint light, very low intensity, and that low intensity absorption also will result in change of current from 20 microampere to, let's say, 50 microampere. So as long as we have change in such current, then we can see that light radiation, that particular light radiation is like exists, that particular light radiation exists there in that photodiode. So yeah, this photodiode is used as a like detector of light detector in many scientific instruments. In many scientific instruments, this is used as a detector. Okay, so we will stop there. Now let us discuss what is called Newton-Raphson method for finding out the roots. So before we get into that, let's see what do you mean by the roots of a function. Suppose this is a function of x and this is x-axis. Now, if the function of x intersects the x-axis at this point, this is the functional curve with respect to x. So at this point, let's say your x n here, it intersects the x-axis. It intersects the x-axis means at x equal to xn, the functional value is 0. Okay, so this point where the functional value becomes 0 is known as the root of the function. Now let's say I have for example, what is that, x minus 1, x minus x plus 3, for example. Just a minute, let me multiply this will be x squared plus 3x minus x minus 3, right? 0. So x squared plus 2x minus 3 equal to 0. All right, so suppose I have a function f(x) equal to x squared plus 2x minus 3. X squared plus 2x minus 3. How do we find the roots? What are the roots of this function? You can find the roots of this function, if you remember, by writing x squared plus 2x minus 3 equal to 0. Then what the method you are applying is that the multiplication of two numbers has to be equal to minus 3. Then the addition of those two numbers has to be equal to this. So you have to write it like that. So which are 3 and 1, right? So you can write this as x squared plus 3x minus 1x. So 3x minus 3 minus 1 is 2. 3 into minus 1 is minus 3, right? So you can write it like that. This is how you solve it. And this will be x squared minus x plus 3x minus 3 equal to 0. So if you take x as a common factor here, x minus 1 plus 3 as a common factor, x minus 1 equal to 0. So this will be x minus 1, x plus 3 equal to 0. Now what are the roots here? The two roots are x1 is equal to 1. The second root is x2 equal to minus 3. So you see that this function will have two roots, x1 equal to 1, x2 equal to minus 3. It will have two roots, right? So that means if you put the root value x1 here you see that your function fx is x squared plus 2x minus 3. Let's say the roots at x equal to x1. What is your x1, your first root here? This is 1, right? If you put x equal to 1 here, what is the functional value now? F at 1 will be 1 squared plus 2 into 1 minus 3. So this will be 2 plus 1, 3, minus 3, it will be 0, right? So let us check at another root, that is minus 3 here. At x equal to x2, which is minus 3, f of minus 3 will be minus 3 square plus 2 into minus 3 minus 3. So 3 square is 9 and minus square is plus. So this is 2 into 3 is minus 6 minus 3. So this is also 0. Now you see that when we talk about the roots of a certain function is that particular point along the x-axis at which the functional value becomes 0, isn't it? At which the functional value becomes 0. So that is what we are going to find out using numerical techniques. This is an analytical technique. You can work it out using your pen and paper, but in computers you are not able to do all these steps. So in computers you have to utilize a certain numerical tools for obtaining the roots. Okay, numerical tools for obtaining the roots. That's what we are going to employ. All right. Now all right. So see, this kind of simple functions you can do it using pen and paper, but if you have some other functions like very complicated functions, for example, fx is equal to 3x to the power, for example, 3x to the power 16, 3x to the power 16 plus 3 root x minus 2 x to the 2x to the power 3 upon 2 and all. Suppose you have this kind of function. You cannot do it, you cannot calculate the roots, you cannot find the roots of this function using your numerical like analytical steps, using pen and paper. If you are going to use those analytical tools to find the roots, it's going to be too complicated, and I don't think there are analytical tools for finding out the roots of x to the power 16 and all. Okay, so in such case, we cannot use our pen and paper, we have to use a computer. So a computer technique, a programming technique for finding out the roots of a certain complicated function is one of the technique is called Newton-Raphson method. So the Newton-Raphson method is quite simple. Let us study the Newton-Raphson method. Suppose we have something like this. Suppose you have a function fx and you have x exists here. Now, let's say your function is a straight line, for example. Function is a straight line. Now, you just take this 2 point, let's say x1, let's say x2. So at x1, what is your functional value? F of x1. What is the functional value here? F of x2. Now, how do we find the slope? The slope will be f of x2 minus f of x1 divided by x2 minus x1. So if you decrease the separation, the slope is equivalent to in analytical approach, slope is equivalent to differentiation of this function df upon dx. Yeah, so this is f of x2 minus f of x1 divided by x2 minus x1, and differentiation we'll just use f prime x. F prime x is your function f of x2 minus f of x1, x2 minus x1. All right, now instead of taking this point x2, suppose I choose the 2 points like this. Let's say this is your f of x. Let's say I choose one point x0. Let's say I choose another point xn here. So this is this point will be your f of x0 here. Xn, your f of xn will be 0. Now if you use the same formula that we derived for these 2 points here, f prime x will be equal to, see, f of x2 is this point here, so this point is your x0. F of x0 minus f of x1 is the point closer to the 0 value. So f of x1, so instead of x1 we are now using xn, so your f of xn divided by x0 minus xn. Now if you write this, f prime x will be f of x0 divided by x0 minus xn, because f of xn is 0 here, because we are taking at the point where the functional value is now 0. Taking the point where the functional value is now 0. So the roots, the xn value will be x0 minus xn will be f of x0 upon f of f prime x, f prime x0. So this is your x0, right? So this will be x, let me write here, the root xn value will be x0 minus f of x0 divided by f prime x0. Okay, so this is the formula we're going to use here. As you see, xn is the root. At xn, the functional value is 0. So in order to obtain xn, we are going to use this formula. Wait, right, I'm going to need another blank space. Just a minute. So I have used up all my blank space. Create another blank space. Okay. Now, yeah. Now let's say we have our function, the one we described before, fx equal to x square. What was that? X square plus 2x minus 3. X square plus 2x minus 3. It has two roots, right? So the functional form may be something like this. Something like this. Okay. This might not be the functional form, but exactly. But let's say this is something like this because it has two roots. So in order to arrive at this point, let us choose certain arbitrary point, random point. Okay. This is called initial guess. Initial guess for the roots. So we'll just give certain arbitrary initial guess. So the initial guess, the initial point that has given us x naught. Now, at this point, you will find your f x naught. This will be your f of x naught. And then you draw a tangent to this. Tangent, that means a straight line. So if you draw a tangent that is a straight line, like we did before, like this thing, if you draw a tangent at this point, then this will be your xn, right? For how do you find your xn? Xn, because this is straight line, xn will be x naught minus f of x naught divided by f prime x naught, right? Using this formula, we will arrive at this point. So we will see that the difference between x naught and xn minus x naught upon x naught is still very large. It is still very large, right? Very large gap is there. Now, if the gap between x naught and xn is still very large, then we will do the next iteration. So in the next iteration, we will assign this point as your new arbitrary x naught. We will assign this as your x naught. So in the next case, we will put x naught is equal to xn. That means xn value is assigned as x naught, semicolon, right? X naught assigned, xn is assigned to x naught. So whatever xn value, we will assign it as x naught. So this is our x naught. Then we will calculate our fx naught again. After calculating fx naught, functional value at x naught will be over here. This will be your fx naught. Now, if you have this as your fx naught, then you draw a tangent at this, you get a straight line. So you will get a new point. Your new point is, according to this formula you are going to use, this is for the straight line. This formula, you remember, it was for a straight line. So this straight line you are drawing here. So for this straight line, you can obtain this, you can use this formula. So this will be your new xn. Okay. Now you will measure the difference between xn and x naught. Xn and x naught gap is still very large. Then you go again to this iteration, say that this new point, your xn, is now your new x naught. This is now your new x naught. Then find your fx naught. At this point, your fx naught will be, the functional value will be this. This would be your fx naught. Now, if this is your fx naught, then at this point, you draw a tangent again. Something like this. All right. So this would be your new xn. So new xn, you can find out this using this formula. Once you have new xn, then you consider the difference between these two consecutive points, x naught and xn. It is still very large. So you do the next iteration, say that this is your new x naught using this command, x naught is equal to x naught is assigned, xn is assigned to x naught. So using this command, you can assign this point as your new x naught, and then find your fx naught again. Your fx naught would be something very small now. Then you draw a tangent line here. So here you will find your new xn will be your new xn will be something very close to this. So as you see, as you continue your iteration, the gap between the new point xn and the guess point x naught is getting smaller and smaller. So subsequently, when this consecutive point in the iteration is becoming very, very small, then you will arrive at this point, the roots where the functional value is 0. You will arrive at the point where the functional value is 0. Okay, that is the numerical techniques. Now, we will use the program. We will stop this sharing, and then where is the dev C++? We will write the program and then we will explain. Control N. You cannot see the screen? Yeah, I forgot to share the screen. Okay, I hope you are able to see the screen now. So the one we discussed was x square plus 2x minus 3. So we have to find the roots of this thing. In order to do that, here we will use x square plus 2x minus 3. The differentiation of x squared plus 2x will be 2x plus 2, isn't it? The differentiation will be 2x plus 2, 2x plus 2. The differentiation of x squared plus 2x will be 2x plus 2. Okay. So type this program. Yeah, this will do. Run this program, you will get the result. Oh, there has to be comment statement, sorry. Comment statement. Forgot to put comment there. You can take any initial guess. Let's say we take initial guess of 6. The root we arrive at is 1. So this is the root we arrive at. If you, I think our time is almost up. We can start another session in just few minutes. I will complete. I will have to explain the numerical code. What is this? How do I stop this? Something is wrong. I have to get this thing out of my screen here. Compile and run. What? Did I do any mistake here? Permission denied. Execute compile. That's something is wrong with my C++. Let me close this. Oh, I think it's already open. That's why. Wait. It's already open. That's the reason. I've already compiled. That's the thing. So if I compile and run this, okay, it's already there. So suppose I go to the manas side, manas 6, for example. Oops, what is wrong? Yeah, now it's working. Let's say go to the manas side, manas 6 arbitrary, then you will get the root as manas 3. So you can get the two roots. Here, when I run the program again, the root I obtain is manas 3. So I will start another Zoom session because the present Zoom session is almost over. How many minutes we have? I think it's very low now. Yeah. How many more minutes we have? Yeah, we still have 4 minutes. I think we can finish in 4 minutes. Yeah. So I have uploaded the result. When I compile this, this is there in your WhatsApp group. So in this program, if you see, this is the new usual IO stream, and this is the usual CMAT. And here we define what is called the error limit. We can define the error limit as, you can give any name. Here I just simply give EPS. You can write error or anything. So the error limit is 0.0001. And you can define the function like this. Your fx here in this case is POW x comma 2 means x square plus 2x minus 3. So our function we define here, fx value is x square plus 2x minus 3. And we can define the differentiation of the function, your f prime x. So instead of f prime x, we will simply write f dx. F prime x will be differentiation of x square plus 2x minus 3 will be 2x plus 3. So 2x plus 2 is your f prime x. Okay, this is your f prime x. So again, the usual declaration using namespace std and all. Then you can define the variables. You can define the variable count as an integer. You can define the variable x naught, xn, fx, fdx, fxn as floating type variables. Then you can write a command for entering the initial guess, that is console in get from statement greater than x naught, and then you can start your count. The number to count the number of iterations, you define your count as an integer. Count, the initial value of count, you just take it as 1, the first iteration, right? Then you put a begin statement here. Okay, begin statement. And then after begin statement, you calculate your fx naught. So here you enter your x naught initial guess. So fx naught will be fx equal to, fx will be your fx naught. Okay, fx will be your fx naught, f of x naught, because here f of x we define in line number 6. So using this f of x function, we can just call the function which is defined here in the line number 6 as this f of x naught. Then we calculate your fx, right? This is your f prime x. F prime x, you define it as 2x plus 2 here. So your f prime x will be f dx. F dx will give me your f prime x. So f dx naught, f prime at x naught. Then you calculate your xn. It's like the formula I described. Xn is x naught minus f of x naught. This is your f of x naught divided by f prime x naught. So your f prime x naught is f dx here. Now you can define the new functional value, the functional value at your xn. The functional value at your xn is this. Okay. Now you put a condition, if statement. You use a if statement. In the if statement, fabs means absolute value. Absolute value of xn minus x naught divided by xn. So if the absolute value of xn minus x naught is less than EPS, the error, if it is less than if the absolute value or the difference in between x naught and xn is less than your EPS less than 0.0001, that means the 2 points, the two consecutive points x0 and xn are now very, very close point. So if they are converging to one particular point, if they are, the difference is less than 0.0001, then you can print approximate root is this, and functional value at the approximate root is this, and the number of iterations you can do. Otherwise, if the absolute value, or if the difference between the two consecutive points x0 and xn is still greater than